I don't have any nice pictures like Juan, so I'll just go ahead and talk about some words. All right, so I'm supposed to talk, and it's going to be cut down to 20 minutes or 15. I'm going to try to do this. I was having trouble this weekend, but we just lost about 10 minutes here. So, okay. Okay. All right. Well, let's just get going. So I'm going to talk about modeling simulation education. My background is I was out here for 30 years as a flight controls engineer. Know a lot of folks at Ames, worked with them over the years. Before that, though, I taught in the early 70s, taught physics and mathematics in high school. And I've served on a school board, and I've advised the governor's office in Virginia on STEM initiatives and particularly what we need to be doing today versus what we were doing in the 1960s as far as science and math and engineering education. So I'm going to talk a little bit about, so that's my background that motivates today. I'm going to talk about engineering, the difference between the E and S of STEM a bit, and Juan used the terms engineers and scientists a bit, and I'm going to expand on that a bit so you understand where NASA is and where the engineers play in all this. And I'm also going to talk about modeling and simulation to some degree. So the first thing we learn, and this is, I think, important for everybody in education, if you want good STEM standards, these are content standards in your state or the guidelines by which you teach, you can't just use K-12 teachers and the Department of Education folks or School of Education folks. You really need to involve practicing scientists and engineers. So in 2007, we did that. We brought practicing scientists and engineers from universities, from government labs, and from industry, and we asked them about the science standards in Virginia and the engineering standards. And lo and behold, we found out there were no engineering standards because engineering is a CTE program and really not available to many kids and not required of anyone. So the first thing is, when you're deciding what is taught, you really need to have people who do that type of work, and those are subject matter experts. As a result of what we did, we got a number of things. For example, we found that Virginia standards, while very well written and highly awarded by the Fordham Institute as great standards for the nation to emulate, were dated to the 1960s. They were Sputnik-era science. Our nucleus in Virginia, we learned the nucleus was made of protons and neutrons, 1918, 1932. We do not talk about quarks, which was 1964. We had no nanotechnology. We had no modeling and simulation as a method of analysis. Organic chemistry, the basis for molecular biology, had been removed from our from our chemistry standards in 2003, according to somebody at the Department of Ed, because the teachers had a hard time teaching it, so why even make it a standard, as opposed to make it a standard and train people to teach it. So this is some examples of modeling and sim content standards that we have. We have them for all middle school and high school science courses in Virginia. You can just look at what they say. Basically, it says modeling and simulation is important. You need to use it in your laboratory investigations. Here's a static picture of the really nice animations that Juan had. And the purpose of this is just to follow on Juan's example and say modeling and simulation is used by engineers, in particular at NASA. And here I talk about rocket scientists and rocket engineers. NASA, we always hear about rocket scientists at NASA. Well, we have very few rocket scientists. We have a lot of rocket engineers. The difference being that science is about discovering the nature of things that are, understanding the world that is. Engineering is about designing the world you would like. Engineering is about solving a societal problem, bringing something of value to society. So NASA has some scientists, but we have more engineers. Many of the things Juan talked about are done by engineers. For example, if you want to find, my example, and Juan can correct me because I'm just from the outside, but if you want to find out if there's life on Mars, do an experiment. Is there life on Mars? And so you go to a scientist and say, what do I have to measure to find out if there's life on Mars? That's the purpose of my mission, is there life on Mars? And the scientist will say, you have to measure this, this, and this, and you have to measure it this well. Well, at that point, an engineer kind of takes over and says, okay, I need to build an instrument so the scientist can get this data. And the engineers go off, and they talk to the scientists. You don't do this in isolation. You talk back and forth. But builds this instrument with some technicians, and he comes back and he says, hey, I got an instrument that can do what you want. Of course, the instrument weighs about 3,000 pounds. And then and so the scientist says, hey, that's great. You know, that's great. But then you have another flight project engineer who says, well, that's not so great because it can't weigh more than 5 pounds, or to put it in mass, 2 kilograms or something like that. And you go, oh, so then the engineer goes and he changes things around. He says, well, he goes to the scientist and says, I've got limits now and I can't measure what you wanted me to measure, but I can measure this. Is this good enough? So there's this back and forth. This is the way engineering works. You're solving problems. You have a lot of back and forth to get an answer to the problem that is adequate for what someone is trying to do. And then, according to this, you also have lots of other engineering to land the thing in the right place, which Juan showed you, and you have information that came from earlier scientists like the atmospheric density of Mars. How does the atmosphere vary in density? Well, we've had landers go in before, we've had orbital vehicles go around Mars, so we know something about gravitational attraction, any mass concentrations, we know about the topography, we know how, because we've gotten that from earlier missions, and that all goes into making these simulations the engineers use to solve their problem. So just real quick, where does engineering sit in K-12? Again, science and engineering. We all have science. Matter of fact, the policymakers, the National Governors Association, for example, says we need more innovation in this country. Did a nice report called Innovation America. We need more innovation. And the next thing they say is in order to do that, we need more STEM, science, technology, engineering, and math. And the next thing you know, they're requiring your kids to take another science course and another math course. Well, what happened to the E? Well, it turns out that E, engineering, is the parent. The engineering design process is the parent of this innovation, this thing of giving value to society. But we totally ignore it. So we put this chart together out of those teams in 2007 to show where it should be in the schools. And what it does is, if you look on the left we have math and science, which at the top you see are taught almost all as theory. And on the right-hand side, you have the trades, the CTE, Career and Technical Education programs, which are almost all hands-on. And there's really nothing in between. You either do theory and you go to college, or you do hands-on, you go into the workplace right out of high school with some type of NOCTI or national certification. Well, the point is that this really should be a continuum, and engineering is what bridges that continuum. So, and there are plenty of engineering programs around. If you're in Texas, there's a nice digital design program out of Texas Instruments and SMU. There's Project Lead the Way that was started in New York, which goes nationally. There's children's engineering for K through 5. I mean, there's all kind of wonderful turnkey programs. And the quick example I will give as to how does this engineering, this hands-on stuff, which is kind of half hands-on and half theory, differ from the trades, the shop classes we know over the past. Well, in the trades, you think of an automobile repair shop. They teach kids auto repair. So you have a shop, you bring a car in, you analyze what's wrong with the car. You go to the shelf, you get a part, and you replace the part you analyzed was bad. An engineering technologist, one line over, who has hands-on skill and a little bit of theory, can go one better. The engineering technologist can not only go get a replacement part and install it, but that person can go and run, say, a CAD/CAM program, computer-aided design manufacturing program, maybe manufacture a new part to replace the old. If you go one more column over, that's where the innovation sits. In the engineering column, the engineer has knowledge of chemistry and metallurgy and structures, materials to some level. And so she can take this problem and say, look, what I know about, polymers or alloys, I can make a better part. I can make one that's lighter, that may go to higher temperature, that may have less impact on the environment. So that's the difference, and that's the piece I would claim of innovation that's missing, these E's of engineers. So I just want to leave you with that and leave you with this chart. Now, modeling simulation. What's different today from, say, 15 years ago, 20 years ago? Why do we do modeling simulation and we didn't do it so often then? And it's clearly the speed and memory of computers. Computer capability we have these days is amazing. So what this does is allows our kids to stop thinking about point solutions. When I was in school in the 60s, we did what are called tables of values. if someone wanted to show you what the difference was between an equation 2x squared plus 5x plus 8 and minus 2x squared plus 5x plus 8, you sat down and you did tables of values, different values of x, and you calculated the y's, and you plotted all those. And actually what happened was, just as you got all the values calculated, the bell rang and you left. And you never really got to see what the difference of changing that sign was, on the first term. So once graphing computers came along, then kids could actually see. They could change all the values, the coefficients, the signs, and see how those affected the shapes of those curves. Well, now we go a step further. With computers, we can now see the dynamic world, how things develop over time, rather than just a point solution. And as Juan pointed out, and again, we've never met each other, by the way. Okay, so this is I was comforted that his stuff kind of looked a little like this, except better, but it's the same material. So what kids can do now is they can solve problems that 15 years ago or 20 years ago took differential equations, took calculus to solve. An algebra student can now solve equations using a computer and see how these things behave over time. They see the dynamic world as it is. Modeling the simulation, again, you've seen this. I'll reinforce what Juan said, I think almost equivalently. It has two parts. It has a model, a physical or mathematical model that approximates the system under study. Approximates because, as we said about the ball, we see you don't measure things exactly. I mean, there's some limit as to which, so they approximate things. And the simulation, in my world of controls, of flight control, has been approximates conditions the system will experience in the real world over time. So you have this model, and then in the simulation, it moves it forward in time through the environmental experience, or an approximation to that environment. The world of modeling simulation can be totally computational, computer-oriented. It can be totally experimental, wind tunnel models put into the wind tunnel. Or it can be a hybrid, and so a little of both. So computational, example I use always is a Roadrunner cartoon. And again, this idea of animation comes in. A Roadrunner cartoon. Think of Roadrunner, and here's a model. Think of Roadrunner on top of a cliff, or Wile E. Coyote, I guess, on top of the cliff, and Roadrunner's at the bottom of the cliff. And there's a big rock, and Wile E. Coyote's about to push this rock over the cliff. Now, what's going to happen when he pushes that rock off the end of the cliff? It's going to fall, yeah. Why is it going to fall? Gravity, yeah. So you have a mental model. You have a simulation. You have a model in your mind that there's gravity, so when this thing goes, it's going to fall. So you know what's going to happen. That's a simulation you're running in your mind. Okay? It could just be a cartoon where they do that animation, where the thing gets pushed over the cliff and it comes down and hits Roadrunner or doesn't hit Roadrunner, depending on whether he's clever that day or not. Now, that works fine, unless your spouse happens to be a NASA engineer, and particularly a Langley engineer, who would look and say, oh, no, that's all wrong, because the rock didn't accelerate at 9.8 meters per second squared or 9.81 meters per second squared. It just fell at a constant rate because the NASA engineer wants this thing right. Well, for the purposes of the cartoon, it was fine. For the purposes of calculating how quickly you have to move out of the way to not get hit, then you probably need to have the actual equations. And so let me just go. So here's some of the equations you could use, and this is what we saw with Juan's experiment. You could have an animation. You could have something simple like d equals 1/2 at squared. No wind resistance because you're at 50 feet and it probably doesn't matter. But if it's further up, you need to have air resistance. You need to have things like perhaps variable air density coming from like a space shuttle coming in the atmosphere. You need to know how the density varies, or with a Mars lander. And you know how gravity varies, perhaps even. How g varies, the acceleration due to gravity varies. Just depending. So the model is as complex as you need for the problem at hand. And that's kind of the neat thing about engineering. There's no one right answer. You kind of have to converge on an answer that is achievable and gives you the information that you need to solve the problem. Let me run back one. Experimental models are things like wind tunnel models, or the thing Juan showed you that can be used in the wind tunnel or aircraft. A hybrid model is something where you have a mathematical model or a physical model, but combined with the real thing. So an example would be a piloted flight simulator. A pilot gets into a simulator, flies the simulator. Well, that's the real pilot. There's no model of that pilot. The pilot's doing the flying. You go to Chuck E. Cheese and get into one of the little race cars, or you do a NASCAR thing at home. Those There's a model of that race car in the computer, but you're the real driver. So that's a hybrid, and you have all these things. And that's kind of a Monte Carlo in and of itself, because all the idiosyncrasies you have and variables you have are automatically part of that experiment that you're doing. All right, quick example, mammoth game. So what can you do in school? These are from an elementary school book that I recommend everybody get. It's like $16 or so. The Shape of Change by Quaden and Tukotsky. And their elementary school teachers are in the Boston area. And they have things that games you can play. So this is called the Mammoth Extinction Game, actually. And I've just shown this SOLs, the Standards of Learning, how it aligns with some of Virginia's middle school and standards in science and in math, and also world history, social studies. It's not just for STEM courses, but you'll see in a minute why it does other things. So the way this game is played, you have 20 dice. And I've got my dice here. 20 dice, and each die represents, or as we call them in Virginia, fair outcome number cubes, because we can't gamble in Virginia. You can't have dice in school, so they're fair outcome number cubes in Virginia. You have 20 of these, and each one represents a mammoth. And you take this herd of mammoths, the 20, and you roll the dice. And you have kids in groups of 4 or 5, and they roll the dice, and they group them. So this in 3rd and 4th grade is good. You're grouping numbers and dice, the 1s, the 2s, the 3s, the 4s, and so forth. Now, on the 1s, every mammoth, every 1 you have means a calf is born to that mammoth. A 2 means that mammoth was killed by a predator. A 3, the mammoth died of starvation. And 4, 5, and 6, the mammoth just had an uneventful year, went on and lived, and nothing happened. So you remove the 2s and the 3s, you add in another die for each of the 1s, and now you may have 17, let's say, in your herd, and you roll again for year 2. And you play the same. You keep doing this until basically you run out of mammoths. And you will, because this is a probabilistic model. You know, a probabilistic model. The probability that you're going to have a mammoth born in any year is what? 1/6. And the probability a mammoth is going to die is 1/3. You have 2/6, twice as much. So they're eventually going to die out. They will all die out differently. So if you have 5 groups of kids, you're generating data sets that are all different year to year, but in the end, they all have the same characteristic. So it's kind of a neat experiment. By the way, why does it also hit other areas like social studies and prehistory? Well, suppose these mammoths were just in an area untouched by human hands, and suddenly humans discovered this land, and they said, oh, those mammoths are good clothing and good food. I'm going to hunt some of these mammoths. Well, now I can introduce a human hunter. So let's change 4, any 4s you roll, to mammoth killed by a human hunter. And so now there are 3 ways the mammoth can die. So what do you think is going to happen to this curve? Instead of 2 ways, there are 3 ways he can die, so it's going to be steep. Same shape, but it's going to be a steeper curve. And that's what kids can now see this. They generate the data and they get to see it. It's kind of a neat thing. And then there are a couple of other really nice things in that book. One last thing I'll do before I get off here is the obesity model. It's a major healthcare issue. You can use a STELLA program, when I'm going to talk about when I talk to you guys a little later. Again, it's out of the ICISEE. STELLA is the programming language, and it's what's called a stock and flow model. So here it is. This is what it looks like. And you know that obesity, getting fat, gaining weight, is caused by getting more calories in than expending. So this model basically has a block that says body weight, and it has pounds input per day that flow in out of calories per day. And then it has, I don't know if you guys can, hopefully you can see this. And then there's an output called pounds burned per day. And if you look down the bottom, there are 2 places you burn calories. One is due to exercise, which everybody always gets. And the other is just because your body has to stay at 98.6 degrees every day. And so you're burning energy to keep your body. And that's a revelation to some kids. Go, oh, I didn't know there were 2 things like that. And if you'll notice, the one which talks about resting maintenance calories burned per day actually has another line coming into it. The other line comes from body weight, because that's not just a certain amount burned per day for everybody, but the more you weigh, the more cells you have, the more mitochondria need energy, and therefore the more it takes. So there's a limit to how fat you can get, because if you eat the same amount of food each day, eventually it's all going to just maintaining body weight. So the wrap up here is, here's a chart that says if I don't use that feedback mechanism of my body weight, if I just say, okay, it takes 2,000 calories a day to live, I eat 3,000, In 1 year, I'm going to go from 170 pounds to almost 300. It's a linear slope. Here's 4 examples of if I exercise and I put the feedback loop in. You can see that the top one, I'm already down to like 235 pounds at the end of the year. And then I just drop. And so what the kids can do with this modeling simulations, they can play what ifs. Well, what if I want to have a hamburger and a shake, but I don't want to, and I don't want to exercise, or how much can I exercise and how many hamburgers can I have? And you can kind of, figure out how much you can mix those 2 ideas together to maintain body weight or gain weight, things like that. So simulation allows you to do these things, and kids will find all the other factors and make this a better and better simulation as they go along. So finish up with ongoing activities. We are developing what's called a flex book, a modeling simulation flex book with the CK12 Foundation over the next few months, and hopefully the teachers, I think, will be asked at some point to contribute some lesson plans to this book, so it will be something for high school teachers to get modeling and simulation information from. We'll publish. And also we have an engineer from Langley who's on site in Washington at the Achieve Incorporated. Achieve will be writing the next generation science standards, and she will provide them subject matter expertise in connections to subject matter experts as they develop these new national science standards. How many folks in here are involved, the states are on the national science standards, Common Core type stuff? So Common Core and the next gen science standards will be an example of that. So she's up there working hard to make sure that things are 21st century and not just a rehash of the Sputnik era. There's a picture of a flex book. There's some examples of one from physics, and you can see kind of something from the nanoscale and some particle physics history. And here's again something, where is the nanoscale? So for high school teachers, middle school teachers, what is this nanoscale? Well, here it is. Here are things in the nanoscale, and this is how they compare to other things such as bacteria or meter sticks and things like that. So summary, good. Modeling simulation is used widely by industry and government today, by technicians, engineers, and scientists. And just to reiterate what Juan said, I'm saying that for innovation, engineering, the E of STEM, needs to be folded into the K-12 instructional continuum. There are excellent programs already available, turnkey programs, and also that if you want excellent STEM curriculum, you have to have practitioners involved in the process. Let's see. Timely vetted, customized curriculum. This is the flex book. We will, as we get this curriculum out in the flex book, you'll be notified as we develop this, and we'll ask the teachers to do reviews of this to see how appropriate it is to help vet it for us. It'll be vetted by practitioners for its technical content. We'll ask you guys to vet it for its readability and applicability to the high school environment. And that's it. Do I have time for, where's Celia? Time for a question or no? Good. Any questions, comments? Wake up, Ames. Comments, questions?